We are recording, Mr. Chesser.
Now this time I will not be pausing and throw up my notes, but every so often I'll say, you need to write this down to help you out as you learn and master that skill of how to take good notes.
Okay, quick recap. Which thing is different and why? Yes, Miguel?
Correct me for chemical reactions.
Sure phone up.
Chemical reactions to physical reactions.
Say that again, I couldn't quite hear you.
Chemical reaction and nuclear reaction. Or,
Which
sorry,
one?
chemical change and...
Chemical reactions and nuclear reactions is fine. Okay? Chemical reactions involve what part of the atom? The electrons.
That would be something to write down in notes.
Nuclear reactions involve what part of the atom?
Nucleus.
It's handy because nuclear reactions has the part of the atom that's involved right there in the name. Nuclear reactions involve the nucleus. I wish that, chemical reactions were called, I don't know, electro reactions or something.
Nature reactions.
What happened probably was chemical reactions got named back before we knew about the nature of atoms, individual atoms. And so scientists named them. I'm not sure what the root of chema is, changing, I guess. Chimera means to change, something that can change, or that has multiple parts. So chemical probably came from a different Latin root. By the time we learned about nuclear reactions, we already knew about the nucleus of the atom. So we knew a whole bunch about the atom by the time we figured that out. So we sort of named them appropriately, right? Nuclear reactions have to do with the nucleus. If you'll think about these reactions, the ones that really get the atom involved and end up producing the most energy are the ones that are really down inside and fundamentally change the atom. In a nuclear reaction, the atom changes into different kinds of atoms. Why? What is it that tells you what kind of element or what kind of atom? When I say what kind of element, that's just what variety or flavor of atom you have. What is it that tells you what kind of atom you have, Miguel?
The amount of protons.
It is the amount of protons. The number of protons is how we classify an atom. If I split a nucleus in two, are the two new nuclei going to have the same number of protons? Yes? I have one atom and it has 86 protons. I split it in half. And you're saying that each new nucleus will have 86 protons? No, it has how many? 43 if it divides exactly equally, but probably it's going to divide in a bunch of different ways. If I have all these new atoms with new numbers of protons, are they still plutonium atoms?
Yes.
Who said yes? Why?
Because they come from the same source.
They come from the same source, but they have a different number of protons, and you were the one who just told me.
So, no.
So no, we changed the number of protons. This is transmutation, the thing that alchemists were like trying to find how to turn lead into gold. We're actually changing one kind of atom into another. Okay? Yes?
So, whenever it changes the amount of protons, does that mean it's changing the element completely?
Yes.
But it doesn't have the same properties when it's split, does it? Or is it like
The same properties as what?
as the whatever element?
The new element?
Yeah.
Yes, it totally does.
So let's say we split a uranium atom in half. What would it then turn into?
Well, it would release a bunch of energy, and it depends on how you split it. If you split it directly in half, you should be able to use the periodic table to tell me if you split it directly in half. See if you can figure that out. I'm going to take a side trail just for a second because this question seems to be interesting some of you. Have you ever, raise your hand if you've ever heard of carbon dating or radiometric dating or things like that. It should be everyone in this room because I told you about it last semester. We discussed it. Great. Can I ask you one other thing, since you seem to be a man who gets things done? There's a room behind that screen full of stuff. We were told that before Christmas that that was going to be our own room. And they were just going to, as soon as they got that stuff over there, still got stuff in it. Well, they can sure use this space if they're serious about it. If they're not, then I'm. But that's above your pay grade. They're not understanding. Yeah, but I don't know when you're supposed to be able to move it. I was throwing that by because you seem to be very organized. I know politicians always want to help me. I can't vote for you though, so don't do it on my house. Thank you. Okay, so what'd you get?
If you split uranium in half, you get plutonium. If you split uranium in half, you get silver.
Okay, if you split it directly in half. The problem with that is it's not like they split directly in half. What happens really is, imagine when you're breaking pool balls. It's not really pool balls, okay, but this is the only way we can think about it. When you first break the pool ball rack in a game of pool, and all the pool balls go everywhere, that's more like what's happening when you strike the nucleus of uranium or plutonium with a neutron. And all those neutrons and protons go flying out of it. Yes?
But what if you split like a hydrogen atom in half?
So you can't well, hydrogen atom has one proton and typically 0 neutrons. Okay? If it had 1 proton and 6 neutrons, would it still be a hydrogen atom?
No,
Why not?
because the number of neutrons defines what an atom.
Yeah, so
There'd still be hydrogen.
So if
It's not the number of neutrons that defines it. It's the number of what? Protons. So I'm going to ask that question again. If it had 1 proton, but I added 6 neutrons, would it still be a hydrogen atom by definition?
Yes.
Yes, because it has 1 proton. That's the only thing we choose. That's the only thing that defines what element is. You probably wouldn't find that. You probably wouldn't find something with 1 proton and 6 neutrons, okay? But you might find something with 1 proton and 1 neutron. If you split the proton, I don't know how to split a proton in half. Well, actually I do know how to split a proton in half. And what you would end up with is a bunch of quarks, which are what make the protons. Here's how I know you can break a proton. That's what the Large Hadron Collider does. The big thing I told you about between Switzerland and France and CERN, where they invented the internet, okay? They accelerate protons using electricity. How could they do that?
The charge electric.
Yeah, the electric charge of the electrons, okay, pulls the proton because it's what do light charges do? Attract. And they get these protons going around and around and around at pretty reasonably high proportions of the speed of light, like really fast. And then at the right moment, they take both protons. A single proton we consider what atom? Hydrogen. We call it a hydrogen nucleus because it doesn't have its electron with it right then, but it's still classified as hydrogen. So if you hear somebody say a hydrogen nucleus, what they mean is 1 proton. They get these 2 hydrogen nuclei going really fast, and at the right moment, they ram them into each other. Inside of a box, it's not exactly like this, and part of this is how I imagine they do it, okay? Because I haven't worked at the Large Hadron Collider, but this is kind of how they have to do it. They get them to ram into each other where there are sensors that can pick up what happens when you smash 2 of those into each other. That's literally what these physicists do. They smash stuff together as hard as they can. That's why it's called an atom smasher sometimes. And then just see what comes out. That's their job. I break stuff and see what comes out. I break fundamental particles of the universe and see what comes out. And that's how we found evidence for things like the Higgs boson, which is sometimes called the God particle. Okay? Which most physicists hate the idea of it having been called the God particle. There's an interesting article you can read about that. Yes, we
I
go.
have a question. So back to when like I just break an atom or whatever.
An atom or a proton?
No,
An atom.
you said that if it breaks apart, it makes it to more obvious what's going on. But how the atoms will change and like if it was a high, let's say it was like atom. Okay, my point is, whenever a bomb explodes, there's
Hold on.
radiation. Is that why there's radiation?
There's a nucleus. This is called a fissionable nucleus because it's big enough. Fission just means to split. We use the same word in biology. In fact, it comes from biology. When a cell divides, we call it fission. It just means to split. So that's all fission means, F-I-S-S-I-O-N. Not F-I-S-H-I-N apostrophe is a different thing, okay? That's fission. This is fission. Okay, this thing splits into multiple different things, okay? They're called the fission products. Okay, they are radioactive. All radioactivity is pieces of this thing flying off on its own. Now, sometimes radioactivity happens because we make it happen, but plutonium and uranium are radioactive on their own. And what that means is this, and this is where I was trying to get to with the radiometric dating, so that's a fine question. If the nucleus is big enough and unstable, it's slowly losing, basically what's happening is over time, the protons turn into neutrons. And when they do that, they spit out some radiation and particles, okay? That spitting out of radiation and particles is what you can detect with a Geiger counter. That's what radioactive means. It's called radioactive because when they turn from a proton into a neutron, they're releasing energy because some of the mass is lost directly to energy following the Einstein equation, E equals mc squared, okay? And what is happening is they're turning into light, some version of light. That's what the electromagnetic spectrum is, okay? You can't see that light, but you can pick it up. It comes out in radio waves. Radio waves are light. It's just a spectrum of light that you can't see. That's why it's radioactive, because you can pick it up with a particular type of detector. It's not actually just radio waves. It also comes out as X-rays and various other things that can harm you, which is why radioactive material is dangerous.
Why does it harm us?
Well, are you bird dogging me now, or do you really want to know?
Well, no, because like, you know how
Here's why it harms you.
Who did the X-ray died because of that?
Yeah, there are various reasons it could harm you. One is if there's enough of it, it can just straight up cook you. Okay, it heats you up, okay? But what happened to Rosalind Franklin, which you're asking with the X-ray crystallography, probably, they didn't know enough about this stuff, how dangerous it was. What happens is, and this gets into biology, in the nucleus of your cell is your DNA, which is a set of instructions which tells your cell how to build new cells that turn into you, okay? Sometimes these particles and energy radiation parts that come off, if they hit your DNA is just made of more atoms, okay? If they hit your DNA just right, they can change it in such a way that it gives you cancer. All cancer is the DNA has a limit on how often it'll tell your cell to make a new cell. And if you change that limit, so it's like, oh, I'm going to start cranking out cells all the time. Your cells could be dividing and making new cells all the time. Your skin cells are doing that. You guys' cells, especially your bones and muscles, are all doing that at a high rate. That's what your hormones are telling your body to do. Mine stopped, except these apparently. So your cells are still dividing. All cancer is uncontrolled cell growth. A cancer in your body is your own tissue. But the genes have been changed so that it's just making a whole bunch more cells that aren't doing anything that help your body. That's what a tumor is. It's a collection of these cells. Okay? So the radiation can alter your DNA in that way. And so the more radiation you get hit with, the more the odds go up that it's going to accidentally hit that spot in your cell and give you cancer. Does that make sense? Mm-hmm. Okay. So this is literally turning into a different kind of atom because you've changed the number of protons in that nucleus. Okay? Sorry, we got off into nuclear physics for a minute there. I apologize, but go ahead. That'd be great.
All right.
You want me to unplug this?
All right, so I changed my mind. I will show you my notes. So we will make certain everybody has the right information because science teachers are gone next week.
Hold on one second. We just ended up having a bunch of discussions that weren't exactly about chemistry, okay? Ms. Court still continued to take notes, and some of you still continue to take notes. All of you should have continued to take notes, and here's why. Even though that discussion was about nuclear physics and it wasn't exactly about chemistry, it turns out that since it's about atoms and how they can change, that it's about chemistry, okay? And some of the stuff that I tell you, everybody's always saying, those children know so much stuff. It turns out that I don't necessarily, I haven't just read tons of material, I have read some stuff. But mostly, what I can do is I know enough of the rules of the system that when asked a question, I can look at the rules in my head and go, well, what would happen if you did this? And so kind of on the fly, I can tell you, well, then this would happen. So you don't have to memorize the whole book, you just have to know the rules. It's much easier. So that's what we just had a discussion about, was a bunch of rules. And if you know those rules, it'll make everything else way easier. So, go ahead, sorry.
Well, I'm going to have to check to make sure. So, from the conversation, what I got was that if the nucleus was big and unstable, over time the protons turn into neutrons and they spit out energy and lose mass. They're turning into some version of light, which might not be visible to us humans, and this is radioactive material.
There is more going on in the nucleus than that, but I didn't tell you about it, so yes, that's totally fine. Anything I say on this too, you know, it's possible that I have some detail slightly wrong. Again, I'm not a nuclear physicist, okay? I just know some stuff about this. Yes?
So, in a nuclear bomb, are they containing a little machine type deal that will split the atom and then cause the, or how does that work? Because they don't split the atom and retain the energy.
So, nuclear weapons today, used by big powers like the United States, don't do fission.
Like little fusion and
Good. So, hold on. Let me tell you how efficient the old bombs were. Okay? You remember I said it's like you hit a pool ball and it hits all the other pool balls and they go flying out? What happens is those pool balls fly out, those neutrons and protons fly out. Now, when a proton is going at the nucleus, it's going at the speed of light, okay? When it goes towards the nucleus of another plutonium atom nearby, what happens when the proton goes near? It repels. Very good, Hunter. And so the protons don't tend to ram into the nuclei because when they get close, they go whoop, or zing off a different direction, okay? But when a neutron goes near the nucleus of another plutonium atom, what happens? Yeah, there's no repulsion and there's no attraction because it doesn't have a charge. So it smacks right into them like the cue ball. I always think of neutrons as cue balls in my head because a whole bunch of cue balls, all the other protons go woo, and they go flying off somewhere else. But or helium nuclei, or hydrogen nuclei, we can call them that too, right? The neutrons smack into another plutonium nucleus. Well, when you hit those cool balls, they all go flying off too. And we get something called a chain reaction. If you have enough plutonium in the area, that they hit these shatter and hit these, and you get this super huge explosion, like Hiroshima or Nagasaki.
So that happens like after they drop the bomb, they don't do it before. And then
Correct. And it's not a machine. There's a couple of different ways you can do it. Because the material is radioactive, that's happening spontaneously all the time. But if you don't have very much of it, there's not enough for a chain reaction. If you get enough of it in one place, the chain reaction can happen by itself. So one version of a bomb is you have under the amount that you need to cause the chain reaction to happen by itself is called what? Anybody know? Critical mass. Critical mass, when you have enough. So what you do is you have just over half of critical mass over here, and just over half of critical mass over here, and you put something really dense in between them, like lead, so those pool balls ram into the lead nuclei and don't set anything off. And then you pull the lead shield out of the way, slap those two things together, suddenly you have what? Suddenly you have critical mass and the thing goes off. Okay? The other thing you can do is, if you have some way to fire neutrons at them, you can just fire neutrons at them until you hit a pool rack, right? And the thing goes off.
How do they like focus the neutrons to shoot them? How can you shoot something
Yeah.
that you can't see?
This is a part where we get into nuclear physics that I don't know. Okay? I don't know how Fat Man and Little Boy work. I think they have different, those are the names of the bombs we drop. Today we don't do it that way at all. Today we don't even do fission. Fission is actually the problem with fission is as the thing explodes, the uranium, the plutonium gets farther and farther away from other plutonium, and eventually the reaction shuts down pretty quickly, actually. All the plutonium doesn't go off. Okay? So the bombs today use fusion, and they use hydrogen, and I don't know, I think they use protons, and they're actually just slamming those things into each other, but I don't know exactly. There's a couple of different ways they can do it, where they have a mass in the center, and you have an explosion that's like a soccer ball that compresses everything together. But this goes beyond me. Okay, I'm not totally sure how they do that. Regardless of this, in a nuclear reaction, because the number of protons in the nucleus change, you get new what? New atoms, new elements. And by the way, every element in the world, in the universe, is built out of hydrogen. Hydrogen and stars are being fused together into new atoms. And a star can construct every type of atom up to iron. Okay, so if you look at your periodic table, you can see that a star can build stuff as big as iron. After iron, the star ends up shutting down. So then you might ask this question, well, there's a bunch of elements after iron, where do they come from? They can only happen when a star is big enough and instead of shutting down, it explodes. It's a thing called a supernova. And in that super high energy environment of a supernova, it actually assembles all the other elements that exist on the periodic table. That's the only way they can be built, as far as we know. We can build them in a lab, but that's the only way it happens
Why
naturally.
can't they, or why can't stars make anything bigger than atoms?
This is a part that I've read and kind of understood, but I don't understand it well enough. There's an energy cost. Something is happening in terms of an energy cost as the bigger elements are assembled, and eventually it becomes impossible for the sun to produce enough energy to build those elements. You can look it up. I don't remember exactly why it works that way. We know that that's true because we can look at stars. You can actually tell what kind of elements things are by the light coming off of them. It's called spectroscopy. And so we can look at stars, and we never see stars that are creating stuff bigger than iron. And this led to this really weird question for a while. Well, where did the other elements come from? And then people figured out that it must be in supernovas. And I am locked up. No, this is on my computer. Oh, no, it's not actually. let that restart for a second. So, that's all nuclear stuff. Most teachers don't teach this part, okay? Because chemistry doesn't require you to know any of these things. I think that if you know this set of rules and you understand this part of how atoms work, that it turns out to make the other stuff make more sense. So I usually teach it this way. I want you to know the difference between a nuclear here. Now, and somebody see if you can tell me now. A nuclear change, a chemical change, or a physical change. Now you know what a nuclear change is. What do you think a chemical change is now? What does it involve? What? Electrons. See, the nucleus is in the middle. The electrons are way out there. The electrons are much easier to change. You can give an electron away to another atom. You can share an electron with an atom. When you end up doing either of those things, the two atoms end up sticking to each other, and they form a what? What do atoms build? Everybody. Nope. Letters are to words as atoms are to...
Wait.
Wait, I wrote it down.
Molecule.
Molecules. Letters are to words as atoms are to molecules. When atoms begin to exchange and share electrons, they create molecules. And molecules is what you're made of. The molecules are made of atoms, so really you're made of atoms, right? But it's the molecules that actually end up being super important. Okay, did it restart maybe? There we go. No, that's okay. Download. Yeah, go ahead.
So some of what Mr. Chester said, I went back and added to the information that I already had above in my notes. Remember, it's beneficial to not go chronologically, but to go by topics. So you can see that at the top, where I talked about chemical reactions, I added in that it's chemical reactions or changes. Nice system of doing that is putting in a slash. I added in that means that you can share electrons, you can give away an electron, or you can gain an electron.
Wait. Do atoms make up molecules? Evolve.
What's the question? Sorry?
Atoms.
Do they turn into molecules or do they make up molecules?
They make up molecules.
Okay, I'll put it in makeup.
They make up molecules in the same way that letters make up words. In a similar way.
Okay, maybe I get it. And that occurs when the atoms
Yeah.
share, give away, or gain electrons. So in case you were falling behind, you can't, from my notes, you can't just glance up and say, oh, it's the same box, because the boxes may have gotten bigger. Because in my notes, I put it by topics, not chronologically. So that when I go back and look at it, if I want to find something about chemical changes, I'm going to look at the box that says chemical changes. That might have stuff added to it based on tomorrow's information that gets presented.
Okay, I got this working.
That's what you guys do.
Okay. So, we got this, which is fission. This is fusion, okay? And this is happening inside of the sun. So that we have smaller things. What's that, probably? What's that, probably? Neutron. What's that, probably? It's got a plus on it.
Proton.
Proton. What are these?
Neutron.
Neutrons. Okay? So, this is happening in the sun. These things, the gravity is so strong it jams them together, and it creates, what kind of atom is this? Some of you who have a periodic table probably know. We call it deuterium, but what type of atom is that? It's a version of what, how would you know how many what it's got?
Oh, it's a version of hydrogen.
It's a version of, not hydrogen. Hydrogen, yes, sorry, not helium. Hydrogen, yes. One proton is hydrogen. That's a version of hydrogen. okay? Now we name them different things because it's pretty unusual to find a hydrogen with these extra nuclei, but it's technically hydrogen, okay? One proton, it acts like hydrogen. You jam these together. Now, here's the question, is this hydrogen? No, why not?
Because it's got 2 protons.
2 protons. It comes apart pretty quickly and turns into helium, and it throws off a neutron. This is what's happening inside the sun in the very center, okay? Hydrogen atoms are being built into helium atoms. And we know this because of the particular types of radiation, the particular types of light and particles that come out of it afterwards. We've done enough experiments in the lab that we know what that light looks like. And that's the kind of light that comes out of our sun. So we make the assumption that, oh, it's the same kind of light, it's probably the same process. And other evidence makes this sort of hold true. Yes?
So can you like smash any atom together, or can you fuse them all together, or does it have its limits?
Well, it does have its limits, and when we get to the periodic table, I'll show you some. We actually create atoms in the lab. We have, I don't know exactly how they do this. I don't know what this machine does exactly. But they have stuff that they can actually somehow jam particles together until they get these really huge nuclei that are bigger. Basically, they will hold together for like a nanosecond. And I mean literally like a nanosecond. A very, very short period of time. But if they can get it to hold together long enough to measure it and see it with an instrument, and they can do it multiple times, then they can say, hey, we created an element, right? It didn't last very long. It was so unstable, and it lost so much stuff through radiation so quickly that it became a different element really quickly, but it did exist briefly. And if you look on a periodic table, let's see if I've got one of this presentation.
Some of the newer ones.
The ones with like, well, like Einsteinium and stuff like that. Sure. I can pull up a periodic table real quick and show you. It's great. It doesn't work very well on this, unfortunately. Just doesn't look very good. The dynamic one, you mean? So, here we are on the periodic table again. How many protons? 1. How many protons?
2.
How many protons?
3.
Hey, look, it follows the numbers. 4, 5, 6, 7, 8, 9, 10, whatever. Now, you get way up into some weird, these UUs and stuff, and all these. These have been created in a lab, okay? They haven't lasted very long, okay? These probably too, like berkelium, Einstein. Actually, I don't know if the lanthanide series, if they've been created in the lab or not. They may have been. Some of these have been created in the lab, but they've only lasted for nanoseconds. This thing always changes. Why are these numbers and these UUs? What's up with that?